Welcome to qnawire.
In this situation, we're asked to look at figure 54, where we have the top wire with a diameter of 100 meters, or not 100 meters, a diameter of 1 millimeter, or 1.0 times 10 to the minus 3 meters. We call that D. It's suspended in the air due to the two magnetic forces from the bottom two wires. The current in the bottom two wires is I, and it's 40 amperes. And the distance between the two bottom wires I call L, and it's 0.035 meters. The density of copper, rho sub c, is 8.96 times 10 to the third kilogram per meter cubed, which is also going to be useful here. So we're going to calculate the current flow in the suspended wire. In order to do that, we're going to use a little bit of symmetry here. So looking at the figure, you have the three different points, A, B, and C, that kind of form a triangle here, where B and C are the bottom two wires and A is the top wire. So the force on B, or the force by B on A, so the force by the bottom wire on the top wire, and the force by the bottom wire C on A are going to be the same. So what we can say is that F BA is equal to FCA, and we're just going to call this this force per unit length F. We'll just call it F. Okay, and the net force here, we can call this F sub n, then from these is going to simply be equal to, using a Pythagorean type theorem here, we have FB on A squared, which we found to just be F. So this is, let's actually write it out explicitly so you can see formally what's going on. So this is F of BA squared plus F of CA squared plus 2 times the dot product of FBA times FCA, which would just simply be FBA times FCA times the angle in between. So FBA times FCA, multiplied by the cosine of the angle in between. But the angle in between would be 60 degrees from the figure. So this is multiplied by the cosine of 60 degrees. This is all under the square root. Okay, but we said that FBA is equal to FCA, and they're all equal to F. So let's go ahead and include that here. Start a new page since we were running out of room. So now we have F net is equal to the square root of 2F squared plus 2F squared cosine theta, which is 60 degrees. So 2F squared times the cosine of 60 degrees. So I'm going to pull the F squared. Oh, 60 degrees, not 60 squared. Okay, let's get rid of that squared. That was supposed to be a degrees, a little typo there. Okay, so we're going to pull the F squared out front. You square root an F squared, that just becomes F. So you end up with F times the square root of 2 plus 2 times the cosine of 60. So this ends up being F times the square root of 3. Okay, well, what is F? The force per unit length by a wire is, we can just write it as F. So these forces are forces per unit length. These forces per unit length are mu naught times the current that's flowing through the suspended wire. We call this current I prime to separate it, and it's different from the other I. So the I prime is the distance through the suspended wire, or excuse me, the current through the suspended wire, times one of the currents through the bottom wire. It's the same in both cases. They're both I, divided by 2 times pi times the unit length that we're considering, L. Okay. But to balance this top suspended wire, the force per unit length of the wire has to be equal to the force on the wire from gravity. So this force also has to be equal to M times G, and it's the force per unit length. So this is going to be M times G over L. But what is the mass here? The mass is the area times the length, L, times the density, rho sub c. And then this is going to get multiplied by gravity, G, divided by L. Okay, well, we see that these L's cancel. That L is going to cancel with this L. And what is the area? Well, the area here is going to be pi r squared. where R is D over 2. So this is pi times D over 2 squared. That D looks more like an A. Let's make it look like a D. There we go. This times D over 2 squared times rho sub C times G. Well, we know D was the diameter of the wire. We go all the way back. It's 1 times 10 to the minus 3 meters. So both of these F's have to be equal if this is in equilibrium. So we know both sides of the equation, and we can set them equal to each other and solve for I prime, right? So we set this equal to this value here. And then we can solve for I prime in this situation. So I ran out of room on this page, but I'll do it on this page. We find that I prime here is equal to, we have pi times D over 2 squared, right? And then this is going to get multiplied by rho sub C times G, where G is 9.8 meters per second squared. It's just the acceleration due to gravity. Then this gets multiplied by 2 pi L, since that was what was in the denominator on the left side of the equation. Then we're going to divide it by everything but I prime that was in the numerator on the left side of the equation. So this is going to be mu naught, where mu naught is the magnetic permeability of free space. It's 4 pi times 10 to the minus 7 newtons per ampere. You can look that up if you want to know more about that constant. And then this gets multiplied by the current in each of the two wires, I, which we said, if we go all the way back, was 40 amperes. So plug these values into this expression. We find that the I prime current is 173 amperes. And we can go ahead and box that in as the solution to our question.